Thanks for the introduction. I hope everybody had a great day yesterday. My name is Böhm. I'm representing Infineon. That's my company today. I hope you had a good night yesterday. I'm very proud to open up the second day of the 2024 summit. So also a very important event for us as a company. Let me quickly talk about Infineon as a company. Most of you know Infineon. We are headquartered not too far away from here in Neubiberg, in the outskirts of Munich. We are about 58,000 people with a lot of R&D sites, almost 70 R&D sites worldwide, 18 billion revenue. A bit more than half of it is coming from automotive. So that's our very key business. A larger part of the automotive business is coming also from microcontrollers and processors we do for all kinds of different applications. So we deal with RISC-V topics, battery management, inverters, so the latest technologies for electrified cars. We deal with safety critical systems, chassis systems, for example, so think about X-by-wire systems in future cars. We deal with infotainment, with graphics, we have graphics controllers, and last but not least, autonomous driving. ADAS is a big topic for us in radar applications and data fusion applications. So we are kind of exposed to everything, to all kinds of different trends in the market. So basically, with that, we have to constantly think about what is innovation in the market, where can we differentiate, and how to new technologies, also open source technologies, contribute. So looking at mega trends in the market, so what are key mega trends? A very well-known mega trend, which is in a lot of discussions the last few months specifically, but also the 2-3 years before already, is software-defined vehicles. So what is it about? Software-driven features in cars, new software architecture, enabling new features quicker. That's one topic. It's also about the reduction of the number of ECUs in cars, very big topic. So basically, an aim for reducing complexity of the vehicle architecture, complexity in software, complexity in the network, also reducing the weight of the wiring harness, for example. And last but not least, and that's a very, very important factor, it's about reducing cycle times, development cycle times in the market, and that's very true for hardware and software topics. When I listen to the discussion of the past month specifically, a lot of things are about, hey, we have to build the next 3 nanometer microprocessor, we have to build the next great software architecture. So a lot of focus on central car computing. And you can ask yourself, so what about other elements of the car, like the control, the microcontrollers, the microprocessors in the other domains of the car? Are we running out of steam with regard to innovation? Is there any further innovation needed, or are we done? So from our perspective, we are not done, because there's properties in the cars, when you look at dependability, affordability, safety, security, which require a new wave of innovation also in the next decade. So we think as Infineon, combining our technology also with open source technology such as RISC-V is a good way to address these challenges. And let me talk a little bit about what we can do for the market here. So before we jump into the future, let's have a quick look back what happened the past 10, 20 years, specifically in microcontroller, microprocessor technology for automotive. We basically have seen 3 phases. So there was a phase between 2000 and 2010, where everything was about performance. So this was really, we came out of a basically 8-bit world, we went 16-bit, we went 32-bit, we brought the first multi-core controllers. We were working on a lot of real-time features, like improving interrupt latencies, fast context switching. So that was in the center of innovation at that time, because most of the problems we solved were control problems. So performance was the key thing. That's still true today, and it will ever be true. What came on top, and that was between 2010 and 2020, there's additional elements where security came on top, functional safety came on top. Security, so what did we do? We improved the instruction sets of our cores. We gave it security-related instructions. We ended up with complete IP modules like hardware security modules, accelerators for security purposes. So the architecture complexity grew, and there was a lot of innovation coming from the controller side. A big thing, everybody knows that functional safety, so the ISO standard started also relatively simple with a few lockstep cores. and we made it into a pretty comprehensive safety concept, which is the status of today's modern controller architectures, where you have a lot of safety elements in all kinds of parts of the chip. That phase ended around 2020. Since then, there's a lot more focus on software and AI. And we brought also new features. We talked about software over-the-air update and how we can do that in our architecture. We talked about virtualization, hypervisor technologies, how you separate concerns. That's something we baked into our architectures the past few years, and something new the past probably 2 years. AI capabilities also in control, playing a stronger and stronger role, and we have to think about which type of technologies we have to provide where, as well as specific accelerators. So that's a very important topic for us. Looking at that history, 20 years, is there any future? What's next? So what's driving us? So there's, in my eyes, 3 elements which are important. There's feature disruption coming, and I think AI will drive feature disruption. We will see a paradigm shift in how control is done in the car, from today relatively static algorithms to AI-based algorithms. That's a very key topic which will probably disrupt the way we do things in the next decade. There's a very high cost focus, a higher cost focus than ever. Also looking at the competition in the market. So affordability of solutions, in the end, affordability of cars is a very important topic. And last but not least, development speed. So we're looking at a speed of 2 years, 3 years today compared to 5 and 7 years in the past. So that changed tremendously. That's true on the software side, but also on the hardware side. So what's next? When you look at aspects which enable the software-defined vehicle in the future, what's coming? So we see a number of innovation areas where we think, as a company, we have to do something, right? So we talked about performance and throughput. We are definitely not at the end of that journey. So we have to think about what can we do to further improve performance. Why is that important? New EE architectures, we have things like zone controllers, integrating a lot of software functions into a single box. That requires way more performance. And that's why we have to constantly work on multi-core architectures and core elements, which give us that performance at affordable power levels, at affordable cost levels. Number 2, determinism, low latencies, reliability, availability of this is important. That's a picture of an inverter from one of our customers. So if you have to control systems which switch 800 volts at 150 kilowatts, you better make sure that you do that right and you do that in time. Now, these topics will remain important. So real-time behavior, dependability, predictability is a key topic, and we have to build in these mechanisms. Also, we have to think about fault tolerance. There's always fault tolerance or fault in chips. You need to manage them. So that's a very important area. Also, when you look at these powerful systems of the future, there's a difference between a diesel engine which just turns and these systems which switch with kilohertz and hundreds of kilohertz switching frequency in some cases. So that's important. Safety, security, same thing. Diagnostic coverage of these systems is important. So we have to have monitors which can check system performance and detect faults. So that's a very important area of innovation. And security, we think, is disruptive. When you think about other mega trends in the market, like post-quantum cryptography, big topic. This will weaken a lot of the security algorithms we know today. So we have to think about different solutions for that problem. Last but not least, reuse and scalability is a topic. Why? Because these are huge investments of our customer. When you look at investing into a software architecture and reusing it for different elements of the car, that's important because you cannot reinvent the wheel all the time for different types of architectures. Also, scaling these architectures to different cost levels is a very important thing, because an OEM customer has typically different vehicle classes with different EE architectures and cost structures. So we have to provide solutions which can address these different complexity levels, but also cost levels. Trying to map that on different application domains. So you can see we have the classical control systems still, like in the chassis or powertrain domain. This is all about real time. It's about latency optimization. So we have basically specific requirements for each domain. There's another domain which is zone controller, more integration. So there's different requirements. There's power efficiency requirements, security requirements, networking capability requirements. So a controller solution needs to have different properties for that. And then on the high end, when you look about ADAS solutions or car computer solutions, you have again different properties. You talk about vector processing performance, you talk about memory bandwidths, you talk about huge amounts of data. So what these systems all have in common, although, are a couple of properties, and these properties are functional safety, or security, or availability, because you want to make sure that you can reuse these concepts in these different application implementations in the car. There's one aspect I specifically wanted to point to, analyzability. Why is that important? Security calls for protecting the chip against misuse. So we spend a lot of effort on hardening our architectures from the security perspective. On the other side, we and our customers need to have access to the chip resources. We need to understand what's going on. You need to debug software, so we have to have access to resources. So you always have to find the right balance between, do I give enough insight into what's going on the software and hardware side versus protecting the security aspects of an architecture. So when you look at how does a classical microcontroller look like, it's not just a single core in many cases. So there's different core implementations in a classical sense. There's two things you have to do. There's a system management job you have to do, and you use cores for that, or in the past state machines, now cores. That's important for booting the device, doing the memory initialization, doing things like reset management, power mode switching. So that needs to be organized, and there's cores doing that, typically one. And you have typically your application cores, which have to do real-time jobs. You're running a real-time operating system. You want to do task management, so the actual application. So that's true for very many control problems as we see today. Think about a power steering system with a three-phase motor control task. Thinking forward and looking at what's in the market today, and when you look at a battery electric vehicle based on a zone architecture, and we have customer examples like that which are on the road, you get a different task for the microcontroller. So what you see is you have different computational elements which you need to solve. So you still have a job of system management. So you still have to do all your resource management of the chip. That remains important, and there's new aspects coming. It's availability aspects, new power modes in a battery electric vehicle, so more flexibility in switching, so that's important. You still have your control requirements, so real-time control is still there, but with massively more performance. But there's also new things like embedded accelerators. So that starts with security accelerators, but we all have all kinds of data processing accelerators for specific application domains like radar or imaging or things like that. So there are specific implementations for that using cores of specific types. Number 4, you have data processing tasks. So these are application cores which have to handle huge amount of data. So you have specific cores for that. And this is where you have to have memory management support and privileged execution modes, stuff like that, also to run different type of operating systems potentially. And last but not least, a relatively new thing, AI extensions, AI accelerators on our chips require another type of computation with also needs for specific core implementations. So you end up easily with quite a big number of cores on such an architecture. You can build that by using all kinds of specific cores. The beauty of open source architectures, and specifically RISC-V, is you can do all that with a single architecture. That's a value. That's a value for us as a semiconductor vendor, but it's also a value for our customers because you can use the same programming environment, the same development tool chains to do all that. So that's an important asset in the future, and that's why we think one of the innovation pushes for the industry will come out of such technologies in the future. So what are the challenges with that? So basically, when you look at the shells I've just shown you in terms of different computational demands, there's an aspect of system dependability. So what is dependability about? It's a measure for system availability. So you want to make sure that the system can maintain certain functions also in case of failures. So that's an important aspect. So you don't want to shut down your whole system, your whole zone controller or your whole car computer due to a single fault in a specific core, you want to maintain functionality. So there's a term for that which is called graceful degradation. So you want to have core architectures which allow you to build such things. That's specifically true for these 3 inner circles, for the system management, for the real-time control, for the accelerators, because you want to, in case of failure, stop them and restart them. So you need to have things like individual core resets and capabilities to manage such things. So that's something where RISC-V gives us a good building block set to do things like that. On the other side, you have a scalability requirement. You want to build all these things, but you need different types of cores and different instruction sets or instruction set extensions for that. So we want to start with relatively simple things like a simple 32-bit ISA we use for system management, for example. We want to have real-time extensions in our real-time core, so we do something, but there's additional things coming. We want to add things like a hypervisor. We want to go 64-bit maybe for the application cores. We want to have another core property for built-in AI accelerators. So we can scale nicely within the RISC-V technology with core extensions to meet all these different application requirements. So that's a good thing, but it's also a challenge to build that, also to standardize that across the industry. Looking at these technologies, we talked about dependability of platforms and how we can do that with RISC-V. We talked about scalability and how we can do that. One thing is also very important for us, which is open source technology. So knowledge sharing within the community. I'm happy to see 600, 700 people here today. So communities like that drive innovation. That's important for us, bringing new features, new innovation, because that allows us also to focus on how can we differentiate in the application for the customer. How can we do specific things which help certain applications to be more powerful. That knowledge sharing aspect is very important. The power of open standards is very important for us, and that's something we also pushing in the industry right now. That's why we engage in open standards such as RISC-V. So there's other examples. RISC-V is a good example for hardware, but there's more. When you look at the software side of things, there's other open standards coming. There's a lot of talk about Rust as a programming languages. So that's also an important element. We last year announced Rust support for our main controller family, which is RISC. So that helps the software community to build more robust software, to avoid memory issues. So technologies like Rust help, and there's large communities driving that. So these open source technologies become essential for us because we get customers started. You all help to get our customers started. They can use technologies you provide. On the other side, we have to make sure as semiconductor companies and tool companies that we get professional tools at the end of the day, which are qualified and hardened for use in, for example, safety-critical applications. This is something we do where we work with partners to harden these technologies. So what do we do? As Infineon, we have seen our announcements last year where we talked the first time about our RISC-V engagements. We are partnering with industry partners, in that case Synopsys, on IP development. So which additional features, which extensions do we need in RISC-V to meet the demands of our application domains? That's important. What we're working on right now is virtual prototyping, enablement of our customers. So we will have first prototype of a new microcontroller architecture available by end of the year, which we then share with customers for benchmarking, software partitioning purposes. So these virtual prototypes are a very important element in the meantime for development, because that's a key thing to shorten development time. So as customers do not have to wait for silicon implementations, we can use these prototypes and get feedback way faster. We can speed up software development. That's a very important element. So that will come towards the end of the year from Infineon on a brand new architecture we are building right now. We're also working on the other side with tool vendors, because you have to make sure that the ecosystem exists, specifically also for the automotive and industrial domain. So here are some examples of compiler vendors we are working with, for example, like Tasking High-Techs and others. That's also important that the tool side is qualified. We have things like ISO-compliant compiler requirements. So things like that need to be organized in the industry. We have to take care that that happens. That also helps you to have access to such kind of tools at the end of the day for your customers' projects. Talking about industry engagements, so we are happy to basically be in collaborations with other industry partners which share our vision of where RISC-V should go. So you may have seen the RISC-V announcement of Quintauris, where we joined forces with industry players like Bosch, NXP, Nordic, Qualcomm to standardize RISC-V technology for the automotive market. I think that's an important thing because we don't want to have a lot of different flavors in the market. So we need to have some level of standardization because only that allows the software community, the tool community to invest. So there needs to be a business case for them. A business case is where if there's a critical mass on standardization and hardware implementations, so we have to make sure that happens. Quintauris is also seen as a bridge between the open source community and the world of the semiconductor industry, but also the tool world. So we are happy to support there, and we are looking forward also now for the presentations you will probably see later this day, so there's a bit more detailed on what Quintauris will do. I mean, these are very important elements to drive the architecture forward in the market, and that's this connection point of open source, professional tools, ecosystem, and bring it into critical systems like we do. When you think about an X-by-wire system, we have to make sure that this is fully safe, fully secure, dependability at the right cost level. Only collaborations like that will allow us to do so. Then let me quickly summarize. So why are we here as Infineon? So we're the #1 automotive microcontroller company worldwide. We have decided to invest into another controller platform next to the others we have, which will be RISC-V based. We see that as a key element of our portfolio for the future. So there's other core architectures, but RISC-V definitely will have its space and room in the market, so we want to support that. That's for us a very important topic. Why have we decided for that? Because we see it as a very lean and efficient starting point for a new path of core developments in the market, and we have seen the core types which we have used as a company, or the availability of our ARM-based implementations in the market. So these are very well known and established core architectures, very important, also important for us. But we think RISC-V needs to be added. Why? Because I think we need to have a nucleus, a starting point, which we now step by step can expand over the next 5 to 10 years to the new needs of the industry. And the new needs are not only real time, it's about data processing, it's about network capabilities, it's about AI. So we have to have different capabilities of core architectures, which the architectures we have can only partially serve. Last but not least, we also want to shape the industry, not as Infineon alone, but definitely we think there's a clear value in partnering. That's why we are here also today. And with that, we want to shape the ecosystem also on the software and the tool sides, but also on the IP side. So that's in our interest. And with that, I hope for good discussions, further discussions today. Hopefully, Infineon will play a very valuable role in all the RISC-V related discussions in the future. And I'm happy to be back in a few years and to talk about the first automotive chips based on RISC-V. Thank you. I think we have a little bit time for questions, so if there are any, just raise them. Yes, okay.
You mentioned open source several times in your presentation. What are Infineon's contribution to open source communities?
Yeah, basically, we are contributing with our engineering community, which is active in the open source domain, so basically in the non-commercial domain. We are working on these standards. We have outside the typical commercial engagements. We are active in activities like that, and we basically, which is not an open source, but an industry alignment in things like Quintauris, this is where we also contribute because this is how we bring in requirements outside the typical open source activity. So it's when you ask for open source specifically, it's twofold. Our engineers being part of your communities worldwide, and secondly, our contribution to events and organizations like the RISC-V Summit. A question here?
Yes, yeah, here. Hello, yeah.
Yeah.
So you mentioned you were doing standardization about the RISC-V ecosystem. So what kind of the standardization? Some in the tertiary or extension or something like that?
Question is for on which extension we are working?
Yes.
Okay. Yeah, for us it's very simple. There's a very good basis. I talked about the nucleus of what RISC-V can give us today. There will be and have to be extensions we need, where we have to bring in the aspects we have learned over the past 10, 20 years of what we need to tweak. And then this is in the direction of real time. This might be in the direction of safety and security. So there's a lot of automotive domain knowledge we can bring in and we have to bring in. And I think there's also interest of our industry partners to do so. So this is the value we think we can bring into extensions of the architecture and how we standardize those to basically enable a stronger ecosystem out there.
Yeah, I have a question.
Yeah.
So generally we have seen in automotive that you generally have an heterogeneous SOC because some are zone controllers, some are doing FUSA specific things and all. So do we expect, let's say, the first automotive chip or whatever comes from Infineon in future will be this kind of an heterogeneous SOC based on RISC-V, where certain extensions are, let's say, more safety-based, some are more application-based. How do we envision the automotive SOC from Infineon coming?
Yeah, basically, when you look at the shells I've shown you, it's probably difficult to do all that in one step. And what we are seeing, the industry will do that in steps, and so we will do. Why? We have to have a starting point, and a starting point for us, or for many others too, when you look at RISC-V usage in deeply embedded implementations, IP implementations, accelerators. So this is where it's going to start, but we have to go one or two steps further, but it will come step by step. So this is how we would see in implementation. So we don't have a current product plan for a RISC-V product in automotive, but we're building an architecture and aligning that with our customers in the market using that technology, which is a very good exercise for us to see how it resonates in the market, because it's also important that we get the buy-in from our customers, apparently. Last question, okay.
You were talking about usage of open source. I was wondering if you'd explored the use of open source silicon and what role that might play in automotive RISC-V.
Okay, so we are, as a semiconductor player, there's some engagements that we talk, but there's not a real open or engagement in really open source hardware. We are aware of these trends, but at the moment we are focusing apparently on our own product and the IP we need for that and the software components. So that's the focus of our activities. Open source hardware, second priority, put it like that. Good. Well then, thank you for the time, and then let's succeed.